So far, we were looking at what is happening at one point in a tower. Generally, what will happen in contacting equipment, you will have a tower or a tray column, and the concentrations of the solute, both in the gas phase and the liquid phase, or if you have two immiscible liquid phases, it will change along the length of the tower. So, in order to find either the height of the column or to analyze what is happening in a given column, you need to make, you need to see, so the concentration will change along the length. So that we have to analyze for that. So our next topic is the operating line, or the operating line of a contacting equipment. Now the equations which we will develop are very general, in the sense that in this course and the next course, you will be looking at various different types of contacting equipment, like absorption columns, tray columns, distillation columns, extraction columns, and so on. The equations which we develop would be valid for all types of equipment. These are simple mass balance equations. So now generally you could have two scenarios, or well, you can have three, but right now let's look at two. Supposing you have a column. You have gas coming in from the bottom and the liquid coming in from the top, and either solute A is transferring from gas to liquid or vice versa. Or, so that would be counter current flow. Or you could have co-current flow. Both are coming from the same direction and going out from the top, or vice versa from the bottom. So let's first look at the steady state counter current mass transfer. So we look at a counter current case. Steady state, things are not changing with time, they are changing with height. So let's look at let's say we have a column. Now again, be careful about be very clear about the nomenclature. Supposing this is we have some contacting equipment, let's say an absorption column, and we have some gas coming in, and this is point 1, so we'll call this as G1. G1 is the moles, everything is in moles, so this is the molar flow rate of phase G, which G stands for gas, or it could be another second liquid also. So this is the rate, molar flow rate of phase G at point 1. And this is in moles by time. Moles by time or kilomoles by time. And there is some solute concentration Y1 here, small y1, is the mole fraction of A of solute, which is A, at the inlet or at point 1. So this is point 1. In this case, it is the inlet. Similarly, we have G2 here. This is point 2. This is G2 and Y2. Same thing. G2 is the molar flow rate of phase G at point 2. And same thing for Y2. I don't think I need to write it separately, but similarly Y2 is the mole fraction of solute A at point 2. Then we have some liquid coming in, let's say L2 here and X2, and going out L1 and X1. So again L1, L2 are the molar flow rate of solvent at points 1 and 2, again moles by time, and X1, X2 are the mole fraction of solute at points 1 and 2. Now what was happening in the column? Let's say we have some transfer, let's say some material is being transferred from the gas phase, A is being transferred from the gas phase to the liquid phase. So liquid is absorbing, so it's an absorption column. So your mole fraction of the liquid or the mole fraction of A in the gas will be highest at the inlet and lowest at the outlet, and vice versa for the liquid, because A is being absorbed by the liquid. Now, if we call at any point, let's say at any point we have some G and some L. So L is the flow rate of solvent plus the whatever A is in that at any point in the tower. And similarly, G is the flow rate of the gas, which includes the solute plus the non-solute part. Now, is G changing along the height? Yes. What about L? Also changing. So that becomes a problem, because G and L are changing, but the solute free part is not changing. So if we call Gs here as the molar flow rate of solute free gas, then that is not changing. Similarly, if Ls is the molar flow rate of solute free solvent or solute free liquid, then that is also not changing. Let's define another term, capital Y1, capital Y2, capital X2 and capital X1. Capital Y1 and Y2 are the mole ratio of solute to solute free gas or solute free gas or G phase. And similarly, X1 and X2 are the mole ratio of solute to solute free liquid. A is being transferred, so moles of the total gas is decreased. Supposing we have air containing ammonia coming in. So air, and it is being absorbed in water, let's say. So, and we are assuming that air doesn't absorb in water. So the flow rate of the total air plus ammonia which is going up will change. Right? The flow rate of air part will not change.
The flow rate will not change, but then how can we say that mole ratio will not change?
I'm not saying mole ratio is not changing. I'm not saying mole ratio. They are two different. Y1 and Y2 are two different. So let's say here we say that this is any Y here, any capital Y here, any X here, and any capital X here. So so G, small y, capital Y are changing along the length. Similarly, L, small x and capital X are changing along the length. What is not changing? GS is not changing. LS is not changing.
So how can, if there's absorption going on, then how can we say that solute-free gas is constant? Like it will change if it...
No, I'll give you an example. Air is there and ammonia is there. So ammonia is going to the water, air is not air part is the same in the gas. So that is GS.
But its concentration will decrease, like for example...
Mole ratio, concentration, how are you defining the concentration?
So the amount, I mean, of what the air, for example, if air is absorbed in water...
Air is not being absorbed, that is what we are assuming. Air is not being absorbed in water. Ammonia is being absorbed. Air is not being absorbed. If both are being absorbed, then of course there's a different problem altogether. Right now we are only saying that only the A part, only one component is being transferred from gas to liquid.
So that's what we are defining as solute.
Solute is A.
Then the solute is changing. If
Solute is changing, yes, that's what I'm saying. So Y is changing.
the molar flow rate of solute-free gas,
Is constant.
how sir, is getting...
No, I give you an example. Supposing you have 90 moles of air coming in and 10 moles of ammonia in it. So you have 100 moles of air coming in, 100 moles of mixture coming in. G1 is how much? 100. How much is GS? 90. Supposing, let's say, all of it goes away. All of the ammonia goes away by the right time. So how much is G2? 90. How much is GS? Still 90. Okay. Please get your doubts clarified. This is important because this you will come across all the time. This difference between GS, G, small x, capital X, that you should be very clear. Now, what is the relationship between Y, small y and capital Y? Mole ratio and mole fraction. We just did that last problem. Capital Y is, write it general, capital Y is, yeah, what? Small y over? No. How did we calculate mole ratio just now? When we did the... No, just general, capital Y is equal to, in terms of small y. So that is, in terms of Y, only two components are there. Y over. Look at this problem. You have 90 and 10, let's say. 10 of ammonia. So mole fraction of ammonia. So small y is 0.1. What is capital Y? 1 minus. So this is Y over 1 minus Y. And similarly capital X is small x over 1 minus x. And what is GS in terms of G? That you have to work out a little bit. You can work it out, but this comes out to be 1 over 1 plus Y. And similarly LS is L over 1 plus capital X. By the way, this figure 4.7 of page 139 of your textbook has a mistake. it writes capital Y is equal to small y over 1 minus capital Y, which is wrong. So he has made a mistake there. Just this is the correct equation. These are the correct equations. So figure 4.7, the definitions of capital Y and capital X are not correct in the book. So I've called it G, but this could be another liquid phase. So you could have two liquid phases. Supposing you're talking about liquid-liquid extraction, which is not, we will not go into the details here, but in your next course you will be looking at liquid-liquid extraction. So then there could be two different liquid phases, immiscible. But the balance equations will remain the same. So G could be a gas, so this could be either a gas-liquid system or liquid-liquid system. Equations will not change. So again emphasizing that although G, the total molar flow rate of gas and the total molar flow rate of liquid, which we have called G and L as respectively, are changing along the length of the column. In this case, if we are talking about absorption, so if it is absorption, then G is decreasing as we go along and L is increasing as we come down. Okay. But GS and LS are constant. This is assuming that only one component is being transferred. So let's make a balance on any general section here. Let's call this envelope 1. So you make a balance on this. What is the balance? So making a mass balance, on envelope 1. So there is no reaction going on. So we are making a mass balance on component A. So what is the rate of input of solute in this envelope? So A is coming in from here and it is coming in general from here. So how much is coming in? How much is coming in here? No. Work in terms of GS. So this is GS here and LS here. So in terms of GS and LS, what is the rate of input of solute? How much of solute is coming in here? GS is the solvent. GS is the solute free part. Again, work in terms of, just take the units. What are the units of GS? GS is kilomoles of solute free gas times kilomoles of solute over kilomoles of solute free. So how much is that? We just did in the last problem. That in that case we had nitrogen and sulfur dioxide. So we multiplied by the nitrogen flow rate by the kilomoles of SO2 over kilomoles of nitrogen. So corresponding to that, what is it here? GS has, this is the solute free part. This is the flow rate of the solute free gas times capital Y, right, and Similarly, so that is coming in here. What is coming in here? Ls x2 and rate of output of solute from this envelope we have going out here and going out here. So that is Gs times y2 plus Ls times x. So there is no reaction. So this is equal to this. Whatever A steady state, so whatever is coming in is going out. It is just transferring from one phase to another. So at steady state, moles conserved because of no reaction. So we have LSX2 plus GSY is equal to GSY2 plus LSX. And we can put it in different form. GS y minus y2 is equal to LS x minus x2. Again, please make your capital X's and small x's properly. These are all capital X and capital Y. So this equation relates the capital Y versus capital X at any point in the tower. These are the bulk values, bulk quantities. This is known as the equation of the operating line, or this is known as the operating line. So this is the equation of the operating line. It is relating, you could have done it the other way also. You could have made a balance from here to here. Similarly, you could have G1 coming in, GS times X, Y1 plus L times Ls times X is equal to GS times Y plus Ls times X1. So that is also one way of doing it. But anyway, let's look at this. So let's call this equation 1. So this is an equation of a straight line. And on a y versus x plot, what is the slope? Slope is equal to Ls by Gs, and it passes through the point x2, y2. So let's see what is happening on a plot. So this is now in terms of capital X is the mole of A per mole of A free L phase. And this is Y, which is the mole of A per mole of A free G phase. And let's say in general the equilibrium curve would be a curve we were looking in terms of y and x's, small y and x's in the equilibrium curve. We can convert this into capital Y's and capital X's also. Now, so let's say this is x2, and this is y2, and let's call this point P. And so the slope, so this is the operating line. And slope is Ls by Gs. So basically the operating line relates the bulk concentration of the two phases at any point in the tower. That is the definition of operating line. You are talking about bulk phases. Equilibrium line relates the interfacial concentration, which are not measurable. Bulk concentrations are measurable. Operating line relates the bulk concentration in the two phases. At any point in the tower. So as you can see in this problem, we are starting from this point x1, y1. That is the top, that is the bottom part. We are starting from here, and as we go along, y is decreasing and x is increasing. Sorry, as we go down, as we go up. So as we go up, y is decreasing and x2 is decreasing. x2 is the lowest at the top, y2 is lowest at the top. Right? x2 and y2 are the lowest at the top, x1 and y1 are at the highest concentration, because the way we have defined it, the x1 and y1 are at the bottom part of the column, and x1 is more than x2, and so in this case we have x1 is greater than x2 for the example problem, and y1 is greater than y2. So this is a case of the solute being transferred from gas phase to liquid phase. And what is that unit operation called? Absorption. So this is absorption. Okay. Now, if you let's just look at any point. So P and Q are the 2 points. Let's look at any point M in the tower. So that is any point in the tower. What is the overall driving force for phase L? See, what are the overall driving forces? If you draw this line, so this is what? This is the overall driving force in the gas phase. So, so this is the, so this from here to here, this is the overall driving force in the gas phase. And similarly, this is the overall driving force in the liquid phase. What is the, supposing I ask you, what is the interfacial concentrations, what are the interfacial concentrations corresponding to point M? See, you have, again, everything is changing along the length, but right now point M is one point in the tower. Overall driving forces are shown here. What are the interfacial concentrations? For point M, what is the interfacial concentration? How do you get the interfacial concentration? Where is that graph? I don't know whether I have it today or not. Don't forget that curve. This one. This was any point in the tower. What is the slope of this line? What is the slope of PM? Minus kx by ky. So, if you make a line like this of slope, so this slope is equal to minus kx over ky, then that is the, so corresponding to M, this will give you the interfacial concentration. Any doubts? And this will keep changing. So your driving forces are not constant. They will keep changing along the length of the tower. Now supposing we had the other case, supposing we had transfer from L phase to G phase. Again, counter current. Transfer from L phase to G phase. So supposing you want to remove something from a liquid, quite often this happens is that you have a solvent in which you have absorbed something, and you want to recycle that solvent, and you remove it by the term which is called as stripping. So basically stripping, you are removing some volatile material or some absorbed material from the solvent by some gas generally. So this is essentially what is called as stripping. So what will happen in that case? Well, I leave it as an exercise, you can work it out, but basically again the slope will be the same, but your x1, this would be your x1 y1 and this would be x2 y2. So in this case y2 is greater than y1 and x2 is greater than x1. Again, x2 is at the so basically the solute is being transferred from the liquid phase to the gas phase. So your x2, y2 are here and x1, y1 are here. The slope still remains the same. So this is for stripping, and corresponding something like this would be for the, just as we discussed just now. So in this case we could also make a overall balance. In this case, what would be the overall balance? Overall balance is what? Ls x2 plus Gs y1 is equal to Ls x1 plus Gs y2, or you can have that Gs y1 minus y2 is equal to Ls x1 minus x2. So depending upon what is being specified, you can make a balance from any point in the column to the bottom, any point in the column to the top, or an overall balance. It's simple like this. There is no reaction, and supposing everything is given in terms of mass units, then it doesn't make a difference. You don't need to convert to moles. If everything is mass, mass is also conserved. So you can work in terms of mass flow rates and mass ratios. But you can't have mass flow rates and molar ratios. So you have to be careful there, that if you are working in terms of mass flow rates, then there will be the mass ratios and mass fractions and so on. So you can work in either way. Now, what will determine the slope of this line? Coming back to this, what determines the slope of this line? So we have this line. What is the slope? Ls by Gl. So quite often in the absorption problem, it would be specified that, okay, I have this much flow rate of gas and I want to remove so much about it. That is the usual specification, that I have a certain molar flow rate of gas and I want to reduce the concentration of A from this point to this point. So basically you have to find out what should be the flow rate of liquid. So when you change the flow rate of liquid, keeping the flow rate of gas same, what will change? See, supposing this is the column, and you are specifying that you have some Gs coming in, some Y1 coming in, and you have some Gs going out and some Y2 going out. So now Gs, Y1, Y2 are specified, and generally you know that what you want. So this is x1, this is x2. Now supposing you change the flow rate of solvent, what will happen? what will happen to the slope? Yeah, supposing you decrease the flow rate, decrease, and it will go on decreasing. So as you change the slope, this will decrease, and at some point it will either become tangent to this or start crossing this. Beyond that, so that is the minimum flow rate you can use to achieve that separation. We will do that little more in detail after we have done some more of this, but I just wanted to mention it here that as you change the flow rate of the liquid, the slope will change. And if it touches the equilibrium line, so supposing if you have this case, supposing this is the case, this is your operating line, and this is your equilibrium line. So what is happening at this point, your driving force is how much? 0. So at this point when it touches the line, the driving force becomes 0. So you cannot have any more separation. So that is essentially the minimum which you can go to. Now supposing we used mole fractions, because quite usually the specifications would be in terms of mole fractions, but as we saw that it is more convenient to work in terms of mole ratio. Supposing we insisted that we had to work in terms of mole fractions, then what would be the difference? See, supposing, so material balance in terms of mole fraction. So supposing, just as we did earlier, supposing we make a balance on envelope 1, what will be this balance in terms of mole fractions? How much is coming in? How much is going out? Yeah, so making a balance we have, so making a balance on envelope 1, we have G1 or G, sorry. No, if you are making in envelope 1 is G times Y is equal to, Gy plus L2, no, L2x2 is equal to, what is going out? Lx plus G2 Y2. Or we can write this as Gy minus G2 Y2 is equal to Lx minus L2x2. Now if you plot small y versus small x, earlier we were plotting capital Y versus capital X, small x and small y's are the mole fractions now. Those were the mole ratios. So again, let's look at a general curve, which is equilibrium curve, could be a curve. I think in one of the assignment problems, I've asked you to, the problem is that you are given the small, the equilibrium curve in terms of small y's and small x, and you're supposed to find out what happens in terms of capital Y equation. But basically, let's say this is the equilibrium curve. Now, and let's say this is x2 y2, and let's say this is x1 y1. Now the difference is, you can see, what is the difference? So this is the operating curve. Earlier it was a line. So that is a big difference in terms of analysis, ease of analysis. Here it becomes a curve, although you can still work in terms of this also, but it becomes more complicated. So that is the reason why I work in terms of mole ratios, because in this case the relationship between the bulk phases is a curve rather than a line. So we have an operating curve. If the concentration of A in the phases is small, then the variation in L and G is not that much, because so if the concentration of A is small, that means dilute mixture, then what is the simplification? See, you have, let's say, again taking an example of ammonia and air. Supposing you had 99% of air and 1% of ammonia, and you are removing 90% of it. So your flow rate is going from what to what? You had 100 coming in, and you are going out 99 point something going out. So your flow rate is nearly constant, even the total flow rate. So if your concentrations are small, then basically then the operating line is approximately linear. So let's look at one example. So the problem is that we have a countercurrent absorption tower which receives 100 kilomoles of gas mixture per hour, having 15% of a solute A. So this is countercurrent, so 100 kilomole per hour of a gas mixture, and we are calling it, this Y1 is 0.15. That is given, 15 mole percent of A. So the mole fraction is specified as 0.15. Then it is required to absorb 95% of the solute. Pure solvent enters at a rate of 80 kilomoles per hour at the top, so this is coming at 80 kilomoles per hour, and pure solvent essentially means that there is no A in that. So basically you are given that x2 is 0. And the questions to be answered are that what is the equation of the operating line, if the concentrations are expressed in mole ratio units, and B, what is the equation if mole fraction unit is used. What is the equation of the operating? Actually, I shouldn't call it line, it will be a curve, but anyway. So in terms of our nomenclature, we have that G1 is given as 100. And Y1 is given as 0.15. So what is GS? How much is GS? 100 into 100 into no 1 minus 0.15. So that is 85 kilomoles per hour. That is the solute free part. What is Y1? Capital Y1 is 0.15 over 1 minus 0.15, which is 0.1765. Now, so solute entering is 15 kilomoles per hour. How much of it is going out? How much of it is absorbed? 95%. That means, so solute absorbed is how much? Yeah, 15 into 0.95. 95% is absorbed, which is 14.25. So the solute leaving with the gas is how much? That's simply 15 minus 0.75. The rest is going out with the solvent. So what is Y2? Capital Y2? 0.75 over No, 0.75 over? What is the unit of Y2? Kilomole of solute over kilomole of solute free gas. So kilomole of solute is how much? No, kilomole of solute coming out, 0.75 so many moles per hour or kilomoles per hour. How much is the solute free part? 85. So that is simply 0.75 divided by 85, which comes out to be 0.00882. So Y2, so Y1 we know which is 0.1765. Y2 we have just calculated as 0.00882. What is what is X2? Capital X2 is no, capital X2 is what? Small x2 is 0, so capital X2 is, there is no solvent, no A coming in with the solvent, so it is 0. So what is your equation of operating line? So just use that equation, GS times Y minus Y2 is equal to LS times X2. Just put in the numbers. So you have 85, Y minus Y2 is 0.00882, LS is how much? 80. 80 times x minus 0. So that is your equation. So you convert it into the form of y is equal to mx plus c, and this comes out to be capital Y is equal to 0.941x plus 0.00882. So as you can see that on a y versus x plot, this would be a straight line with a slope of 0.941. Now, second part is to do it in terms of mole fraction unit. So, what would that be? How would you do that? Well, simply put in the definitions of y and x in this equation. So, if you substitute for capital Y and capital X in terms of small y's and small x's and simplify, so we have so what is capital Y in terms of small y? Y over 1 minus y, and this is 0.941 small x over 1 minus x plus 0.00882. Now you have to put it in terms of y is equal to x. Y is equal to some function of x. So you just have to simplify. So if you invert it, you have 1 minus y over y is equal to 1 minus x. So this comes out to be 1 minus x. Okay, you can, this is just essentially algebra. And 1 over y is equal to 1 plus this much, which comes out to be 0.9322 x plus 0.00882 plus 1 minus x or y is equal to 0.9322x. So when you simplify this numerator and invert, this is what you get. Y is equal to 0.9322x plus 0.00882 divided by 1.00882 minus 0.0678x. So as you can see that when you work in terms of small y's and small x's, you don't get a linear curve, linear equation, but it's a curve. Then you can plot y versus x. Any doubts? ये बंद कर दीजिए.